Okay, now we're going to talk about how we describe a graph in a computer language. So the first possibility, which I mentioned briefly in class, is the array-based implementation. Okay, in that case, we have a 2D array, which is an adjacency matrix. And if the graph is sparse, that adjacency matrix is going to have mostly zero entries. And so we typically don't like that unless we're looking at a dense graph. So I give an example of a graph on the next page, I draw one of these so you can see it. So in that case, the nodes are a 1D array in the sense that you just have an associative array. So again, without any loss of generality, we can just label the nodes 0 to number of nodes minus 1. And if we want to give them a label, we can just keep a separate 1D array, which in this case gives string labels to the nodes, which are the city names of the endpoints. So when it says a 1D array is used to represent vertices, that's what it means. Well, a 2D array represents the edges. And so this is just an edge from Atlanta. Let's just take Atlanta, for example. Atlanta has an edge to Houston. Atlanta has an edge to Washington. Okay, so Atlanta has those two edges. So, oops. So if we look at Atlanta, it has an edge to, um, let's see, 5 is Houston, and its weight is 800. And Atlanta has an edge to Washington, its weight is 600. And all these other things are just 0. Okay. Or, you know, I don't remember why I put the dots at, they're undefined. So why are they defined? Oh, because these aren't, that's right, now I remember. These aren't filled in yet at all. 0 just means that there is no edge from one to the other. Okay. So you could just create a big 2D array. In this case, let's just say the array, we know the size of the array, and you carry around a lot of zeros. So it's not the most efficient implementation. It is nice to have a 2D array. It's just something that you can loop through quickly and is easy to manage and easy to build. But more typically, you do a linked list implementation like I showed you in class. So you still have the 1D array for the vertices, but then a list is used for each vertex, and it's just the adjacent elements. So you just contain an adjacency list. And that way, if you're connected to one person, you just have one element in your adjacency list. You don't have a bunch of zeros sitting around. So if we look at that same graph, now we say, okay, Atlanta has an edge to 5, which is Houston, of weight 800, and then that contains a pointer to the neighbor. So although you reveal the fact that this is a bunch of pointers, in a higher level sense, it's just a list. So it's just a list of the adjacent nodes to node 0. This is a list of the adjacent nodes to node 1, and so forth. So this is obvious, and that node, that list also contains the weight. Okay, so this is what we did in class, and I think this is, more sensible structure most of the time, because 90% of the graphs you deal with are not going to be dense. Most things are not connected to most things. It's just in my experience. When you model things, you typically deal with sparse representations. So this is sort of what our focus in the course will be. Okay, and if we look at it, we can see what the memory complexity is. So adjacency matrix, I'll just say at a high level, is good for dense graphs. The connectivity between two vertices can be tested very quickly. It's always nice to use arrays. And adjacency list is good for sparse graphs. I'll let you check the limits. They're pretty obvious. And vertices that are adjacent to another vertex can be found very quickly. Okay, so they're good for different things. All right, and I talked a little about the graph data structure, so I won't go over it much here. I just remind you that this edge node is really a node in a linked list, and that linked list is part of the graph data structure, and that pointer just means this is an array. I'm sorry, this max v plus 1 means that it's an array of edge node stars, and edge node stars we think of as just the root of linked lists. Okay, so we keep, again, this max v plus 1 is just because typically mathematically we think of graphs being numbered starting at 1. So some books do that, so I did it that way. And I think everything else is pretty clear. A bool is just true or false. All right. And I went over some of these methods in class. I will upload them to the Dropbox, but this is just a simple constructor. I showed what a file looked like in class, and a file is just each line is just from vertex to vertex weight, and from vertex to vertex weight. So here it is just from vertex to vertex because I didn't include any weights. And so I'm just giving an example of what a read graph might look like for that type of input file that has no weights, or if you just ignore the weights. And I have all this code, so I don't think we need to go through this again. Okay, so that's the basic representation of a graph. Look at the live lecture and look at the code that I put in the Dropbox. If there's anything that's unclear, make sure that you understand the basic implementation, because now we're going to use it to do a bunch of canonical problems. And the first is going to be searching. There's nothing more important than being able to visit every node of the graph, because it's the building block for so many different algorithms, finding shortest paths, finding cycles, so all sorts of things, finding minimum spanning trees. So we want to make sure we understand, and they're always subtle. I think at our level, we're prepared to understand them pretty quickly, but you still want to take your time and make sure you understand them. So next we look at depth first and breadth first search. And in this case, we're going to do it in the context of finding a path between two nodes of the graph, for example, between Austin and Washington. But we talk about the methods generally.